Okay, good morning. How's everybody doing? Good? All right. How is my sound? Is it okay? Because I was having trouble a little bit earlier today. All right. Well, if anything goes wrong, like if the sound goes out, just send me a message here in the chat window. Okay. Let me maybe start with this. I'm going to put here in the chat window the link to the last lecture. So I'm trying to put everything here on YouTube, and hopefully you'll have access this way. So here, maybe I'll just show my screen. So here I just have my web browser open. You just kind of see the YouTube video. So this is just a video from Monday. Let's see. It's not playing. So I think that there's also a channel here. So you can feel free just to sign up for the channel. And I'm going to try to put the videos there. I think that that might be the easiest way to keep track of things. But if you have any trouble whatsoever, then please let me know. Okay, so let's go ahead and get started. First, I guess before we do get started here, I'm just kind of wondering, what are your feelings about Monday's lesson? So in particular, I'm wondering about the slides. Do you like the slides? Would you prefer that I use a whiteboard? So just kind of let me know just some of your comments. So what did you feel about using slides for the first day? Yeah. Zena, say something?
Yeah, I felt like, I don't know if anyone else felt this, but it seemed like with the slides we were going a little bit faster, and I know at least for me that was a little bit challenging. So maybe if we used like writing or just like went slower with the slides, I don't know what everyone else thinks about it, and yeah, happy to adapt.
Okay, right, that sounds good. Yeah, Jean, did you?
I wonder, like for me, I feel like every time you put out a expression or an equation on the slides, it gets kind of fast and it's hard to know what's on the equation. So maybe every time after an expression, you can just give a few seconds to read it.
Okay, that sounds good. All right, any other comments? Okay, let's try that then. So if I do go fast, or if you're having any trouble keeping up, please either raise your hand, send something in the chat window. I'm very happy to slow down here. And in fact, today I actually do plan to slow down quite a bit because I wanted to kind of do some motivation for what we're going to do next. But yeah, please, or thank you very much for those comments. So I believe that the slides are already on Sakai, so you can certainly follow along with what we're going to do here today. So let me maybe just start with just some quick announcements, just to remind you about things. I am going to hold office hours as usual. Just remember that everything is going to be virtual here. So at the end of class today, I'll be around from 11 to 12, and then I'll also be around from 4 to 5, and of course, both Pacific times. And as usual, if you can't make any of these times or have questions outside, just send me an email, and I'm happy to do the best I can to answer things. Also, as a quick reminder, the mentor sessions are now going to be 6 to 8 p.m., Sunday, Mondays, Tuesdays, and Thursdays. So the next one will be tomorrow evening, again, Pacific time. And there is a Facebook group that Suresh has created in case you'd like to play around with that to get an idea of, or I should say, just to have another way to ask more questions. And then finally, as a reminder, the next few homework assignments are due. So I did see that several of you have posted homework set number 9 in the Sakai Dropbox folder. If you're having any trouble, just go ahead. You can send it to me by email. I'm more than happy to upload it there to the Dropbox folder. But the next assignment is going to be due on Friday. And then homework assignment number 10 will be due next Wednesday. Okay, any questions then? Right, great. So let's try to recap the main ideas from Monday's lesson. Really, there were just a couple of big concepts, and it comes down to what's called the monotone convergence theorem. So say that we have a complete ordered field, and you can just think of F here as the real numbers, but remember that we're trying to do a lot of things axiomatically to get a better idea of what statements do we really need to prove things about the real numbers. So first we have the concept of convergence. So this says that if we have a sequence, which we'll write here as the set, so here we're just running from x0, x2, all the way through xn, we'll say that this converges if, given some positive number epsilon, we can find some number delta such that this absolute value here is less than epsilon whenever n is greater than delta. Right? Now, what I'll say is that for the most part for this class, you don't need to do the fancy proofs like what we did before. Right? Before, that was just to say this is how the proofs are going to go, but we are going to try to spend some time over the next few homework sets and the next few problem sets understanding how do you choose delta. So what does this mean? But mainly, I just want you to remember that whenever we work things out here, there are three statements. There's kind of first say, let epsilon be given. Second, you then have to cleverly choose your delta. And then third, you have to kind of prove that everything works. Right? But again, we're going to try to slowly work through this as the course progresses. Now, we also have the concept of divergence, and this was kind of in two parts. First, we can say that a sequence increases without bound if, given epsilon, then we can find a delta such that our xn is greater than epsilon whenever n is greater than delta. So this just simply means that no matter what you give me for epsilon, epsilon could be 1,000, it could be 1,000,000, I can always go far enough out in the sequence where I can make xn larger than epsilon. Right, so again, increases without bound just means I can always go far enough out in the sequence where the sequence gets larger and larger. Next, we have kind of the opposite idea, so decreases without bound. And this just simply says that if you give me epsilon, any epsilon you want, it could be 1,000, it could be 1,000,000, then I can go far enough out in the sequence where my xn is all the way to the left. So maybe like if epsilon is 1,000,000, then of course negative epsilon would be like negative 1,000,000. And then this says that I want to choose my n large enough so that xn is even to the left of negative 1,000,000. Right, so again, decreases without bound means that I can make it as much negative as I want. And then putting these two together, we'll just say that a sequence diverges if either it increases without bound or decreases without bound. So divergence just means that the limit is either positive infinity or the limit's negative infinity. Right. And so if we're in neither of these three cases, so it neither converges nor increases without bound nor decreases without bound, then we'll just simply use the phrase does not converge. Right. Okay, so any questions up to this point? Right. So also kind of moving on here, we had some theorems that related to the concept of being a monotone sequence. So we'll say that a sequence is monotone increasing if whenever we go to the next term in the sequence, it just gets larger. It's monotone decreasing if the next term in the sequence is smaller. And we'll just say simply that it's monotone if it's either monotone increasing, monotone decreasing. Right, so again, increasing just means that the next term is larger. Decreasing means that the next term is smaller. So the main statement here is that we have this so-called monotone convergence theorem. So this says that as long as we have a monotone sequence, then either it converges or it's going to diverge, right? So in the specific case, let's say that it's monotone increasing. So if we have a monotone increasing sequence with an upper bound, then it has to converge. Right? So again, a monotone increasing sequence with an upper bound has to converge. Otherwise, it will diverge, right? So it'll increase without bound. Similarly, if we have a monotone decreasing sequence, we have two cases. If it has a lower bound, then it converges. Otherwise, it will diverge. Right, so again, the whole point of the monotone convergence theorem is that it just says that you really have two things that happen. Either if you have a monotone sequence, either it converges or it diverges. Right? Convergence means that you have to worry about whether you have a bound, or divergence just means it'll either increase without bound or decrease without bound. Right. And then finally, we had worked out this nice example to say if you have a sequence here, x sub n, that corresponds maybe in this way here. So the m term looks like L plus something times rho to the n, and rho here is between 0 and 1. Then we can actually prove that the limit is L by defining a monotone decreasing sequence. So we kind of did this fancy trick here of we defined a new sequence, T sub n, and we proved that this was monotone decreasing. Right, so if you will, this will be a trick that we're going to use later, is to say that if you want to prove convergence of something, you might as well just kind of introduce a brand new sequence and then play around with that. Okay, right, so any questions here on these statements? Right. Okay, so now let's try to move on to the new material. And what I want to do today is kind of go backwards a little bit. There's some things that we skimmed over some weeks ago in terms of square roots. So some of this you'll actually need for the problem sets. Some of this I just wanted to be pedantic and talk about. But I want to go back for a little bit and talk about what is a square root. So simply put, there was a problem set where basically we said the square root of p exists whenever p is greater than or equal to 1. Right? So I want to step back for a little bit today, and I want to go over this in a bit more detail and talk about what does all of this mean. Well, if you are willing to accept that statement, that the square root of p exists whenever p is greater than 1, then you can actually show that the square root exists for any positive number. So here's how you would do this. So number one, let's take d to be something greater than 1. And if you will, I can just set p is equal to d. So then remember that we define the square root as the supremum of this set here. Right, so again, we define the square root of p as the supremum of this set. I want to go over this in detail today to remind you what's really going on here. So how do we know that the supremum here exists? And how do we know that the supremum really is the square root of p? Right, but if you will, this is kind of the definition that we can choose from one of the problem sets. Now, if instead d is less than 1, so let's take this here, then of course 1 over d is greater than 1. So you may also remember that from one of the problem sets. So if I have a number that's less than 1, its reciprocal is greater than 1, and then I can define the square root in this way here. Right, so I'll just define the square root to be the square root of p over p. It's sort of like saying I want to choose 1 over the square root of p. But we'll just define now the square root of a number d to be this here. So for example, how would you take the square root of 1/2? Well, you would want to say it looks something like 1 over the square root of 2, but I can rationalize the denominator and just say, well, it's just the square root of 2 divided by 2. Right, so it's the same idea here. If I want to take the square root of something less than 1, I just do this trick. Now, this, of course, is a nice theoretical statement. It just says the square roots exist, and we'll come back and talk about this. But I have a really simple question. How do I actually compute this? So I'm not so worried about this fancy theoretical way of doing it. I actually want to be able to sit down with a pen and paper and say numerically compute the square root of 2. So I want to say a little bit today behind how does this work? How do you actually compute square roots? So the first thing I'm going to do is define a sequence. So here, let's say that p is given. So p is a number greater than 1, and we're going to look at some examples in just a moment. So if you give me p is greater than 1, I'm going to define a sequence of t sub n, so t0, t1, so on and so forth, recursively in this way. Right, so let me define a sequence of t's recursively in this way. And now I have two claims. Number one, I have a monotone increasing sequence such that the squares are less than or equal to p. Right, so again, it's a monotone increasing sequence where t squared is less than or equal to p. And number two, if my t squared is slightly greater than p, then my next one is also slightly greater than p, but it's a little bit less. Right, so I'm going to try to come back and say what I mean by this here. But again, the whole point here is that I have an increasing sequence of positive numbers that gets such that t squared gets really, really close to p. So we'll define our sequence t sub n in this way. And then now we should have an increasing sequence that gets really close to p. All right, so let me try to say a little bit more about this. So the t's here, of course, I start at 1, and then I go t1, t2, tn, so on and so forth. And because I have this tn squared is less than p, then I know that I have an increasing sequence that has an upper bound. Moreover, what the second statement says, the second part, is that you can actually make the tn's as close to p as you want. All right, so this statement here says that if maybe tn squared is slightly greater than p, then the next one is slightly greater than p, but not as much. All right, so again, if the tn squared is slightly greater than p, then the next term in the sequence is also greater than p, but it's not as much greater than p, so it's a little bit closer. So really, you can conclude that the limit here has to be the square root of p. So here's the reasoning. I can use the monotone convergence theorem to say that here I have an increasing sequence. So let's let S be the limit of that sequence. Right, the monotone convergence theorem says that this limit has to exist. Right, Zintan, did you have a question?
Yeah. So if t squared is slightly greater than p, and then the next one is also slightly greater than p, but by less,
right,
does it mean that the next one is less than the first one?
That's right. Yep. In fact, that's exactly what I was going to say. So say, for instance, if p is equal to 2, then this here would say that maybe tn squared plus epsilon is greater than 2. But now this here says that the tn squared plus a half epsilon is greater than 2. And then the next one will be tn squared plus a fourth epsilon. And the next one will be plus an eighth epsilon. So they might be greater, but they're going to get closer and closer and closer. Right? So that's really the whole point of this part here, right? That I can get as close to it as I want. So remember what we said before about the supremums. So the supremum says something like it has to be an upper bound, but the least upper bound. So this part here says that we do have an upper bound, but this part here actually says that we have a least upper bound, right? Because we can get as close as we want. Right, so in other words, and we're going to come back, I'm going to try to do this on Friday when we have more time, is to say that if we're looking at this set here, right, so the set of elements that are positive, but t squared is less than p. So on the one hand, I think that when you've done this in the problem sets, you probably have noticed that it's relatively easy to show S here exists, right? So here I have a non-empty set with an upper bound. So it has to have a least upper bound, so this element S has to exist. On the other hand, you should also be able to show that S squared is less than or equal to P. Right, so again, our upper bound, our least upper bound has to satisfy S squared is less than or equal to P. What this here shows is I can actually find a set of elements from S where I can get as close to square root of P as I want. So again, I'm going to try to come back and do this rigorously on Friday, but I just wanted to emphasize for right now that this sequence actually does prove that there is a sequence so that the lower bound, so I should say here that the limit actually is the square root of P. So putting those two together, that's why we know that S squared has to equal P as opposed to less than or equal to P. Okay, right, so any questions here? Does that kind of make sense? All right, and again, I do want to come back and talk about this a bit more on Friday. Now, that was looking at a monotone increasing sequence. We can actually do the same thing from the other direction. So again, let's fix your favorite P greater than 1. And now let me define a sequence here where here we have B sub n is 1/2 Bn plus P over B. Right, so let's define this new sequence. And you'll notice that this is a decreasing sequence. So now the numbers here are getting smaller and smaller, but the square is still greater than or equal to P. So sort of like now I'm above and I'm going down, getting smaller and smaller. And just like before, this says that maybe if my Bn squared gets close to epsilon, then I can actually, the next term in the sequence gets even closer. So this is the idea of the infimum. Right, so now approaching from down below. I should say going above, but now going to the left. So again, we have a monotone decreasing sequence. And the second part here says that we can actually get as close to epsilon, as close to the square root of P as we want. So simply put, if we write this sequence, so the set of elements that are positive, but the square is greater than P, then this here would have a lower bound. And so the greatest lower bound is what we're calling the infimum, so that will be S. All right, so again, here we have a set so that its greatest lower bound exists. We'll call this S. And it shouldn't be too hard to prove that S squared is greater than or equal to P. Right, so again, it shouldn't be hard to prove that S squared is greater than or equal to P. But now, here we have a sequence where it says we can get as close to P as we want. So now I've written a sequence for this set that's going to get very, very close to the square root of P. So this is why we actually would have a proof that the infimum is the square root of P, not just greater than, but it is the square root of P. Right, and again, we're going to try to talk about this in a bit more detail on Friday. Okay, so any questions so far? Okay, so before we go any further, let's actually just try to play around with some numbers here to get a better idea of how all of this works. All right, so I'm going to try to pull up my Mathematica, and let me see if I can actually type some things here real time. Let's see. All right, so let me stop sharing, and I'll come over here and share my Mathematica. Right. So what I'm going to do here is define a sequence. Let's see. So first, let's maybe do the t's. So let's define t0 And I guess let me make this a little bit larger. As 1, and then I'll define t sub n, just like the way that we did over here on the slides. So p times the previous one plus p divided by the previous one plus p. And for the moment, let's set maybe here p is equal to 2. Right. Okay, so here we're just going to define a sequence. And let's maybe just try to compute a table. Where maybe n goes from 0 to 10. And the n here just says, I just care about the numerical value. Let's just maybe do. So what I've done now is I'm going to say compute the numerical value of t sub n, compare that with the numerical value of the square root, and let's just do this as n goes from 0 to 4. Right, just to get an idea of how things look. Okay, so here in the first column, this is our n, right? So that's going to be our index for the sequence. Here in the second column, these are the t sub n's. All right, so here we're just trying to look at numerically what's happening. And over here in the last column, this is what the square root of 2 will look like. So let's see a few things here. So here in this column, you'll see that it's increasing. Right, I start at 1, I go to 1.33, I go to 1.4, I go to 1.41. So the t sub n's here are increasing. And also, you'll see that they're getting closer and closer over here to the square root of p. Right, does that kind of make sense? All right, let's maybe try another one here. So I don't know, let's try 5. So here's the same thing as before. All right, so the numbers are increasing. They're getting closer. So let's maybe try to go from 5 to 10 now. All right, so now again, here are the n's. These here are going to be the t sub n's. And you see that they are getting closer and closer and closer to the square root of 5. Right. Okay, so any questions here about this sequence? All right. Okay, let's try to do this now. Let's maybe try to put in the sequence here for the b's. Right, so we said that b0 here is p, and then for the next ones, we said 1/2 to the previous one plus p divided by the previous one. And then let's also try to put in a table here. Now we'll put in b's. Okay, and for the moment, let's maybe start with kind of a simpler case. Let's say like p is equal to 2. And now let's try to do this. Okay, so here, we just started off with b sub 0 is p, because that's what the sequence says. Now we'll try to do the next term in the sequence. So we have to write this in terms of the previous term. And here for our table, we'll list the n's. This says now numerically compute what this is, and then numerically compute what this is. Right, so now let's just try to work out some numbers here. Okay, so here's the n. Right, so this is just the index. Here is b sub n. And then here is the square root of p. So in this case, the square root of 2. So here you'll see that this is decreasing. Right, so it starts at 2, goes down to 1.5, and now it's kind of getting smaller and smaller and smaller. Right? So let's see, let's maybe try another example here. So I'm going to come up here, plug in p is equal to 5. And now let's try to do the same thing. So look at the sequence. Okay. So now you'll see here that here's my n's. Right, here are my b sub n's. So it goes 5 down to 3, down to 2.3, and it's getting to square root of 5 pretty quickly. Right, but it is a decreasing sequence. Okay, so any questions on these numerical examples? This kind of makes sense here? Right. Okay, so for those of you that are into computer science, this actually does give you a way of computing square roots. And here, this just says you can do this in either way. You can either have an increasing sequence that kind of starts at 1 and gets larger, or you can have a decreasing sequence that starts at p and it gets smaller. Right? But either way, this actually gives you a very quick numerical way of computing square roots. Right. Okay, so I'm going to come back over here to the slides. Right. So here what I've done is I've tried to kind of compare a couple of examples together. So here's, let's say, p is equal to 2. And then here's what happens for the Tn, and then here's what happens for the Bn. Right, so you can see here on the left that we do actually have an increasing sequence. Right, so it starts at 1, goes to 1.3, gets larger and larger. But over here on the right, this is a decreasing sequence. Right, so it starts at 2, goes to 1.5. So these two sequences kind of complement each other. Right, so one kind of starts from below and goes up, the other one starts from above and then goes down. Right. And then similarly over here for p is equal to 3. Right, so you can see that here we started at 1 and now we're increasing and go up, whereas over here on the left, or on the right I should say, where we're starting at 3 and then we're kind of going down. Right, but that's kind of what these two sequences do. Okay. So what I want to do next is spend a little bit of time going over how do you actually prove this? So how do you actually know that these sequences converge in the ways that they do? Right. So let me remind you, this was the very first proposition. So we started with p is equal to 1, and then we defined a sequence in this way here. And so I do want to prove these two statements. Right, so let's try to prove the first one. I'm actually going to try to prove this by induction. Right, so the statement that I'm trying to prove is the following. So number 1, we have an increasing sequence. And number 2, that the Tn's here are less than or equal to p. Right, so this is my statement as a function of n. So of course, with any proof by induction, we need to do 3 different statements. So first, let's do the base case. Well, of course, we've chosen t0 to be 1, and we've chosen p to be greater than 1. So at least we have these first 2. Now let's take a look at the next term, maybe t sub 1. Right, so here I've just computed t sub 1 just by using the formulas up above. Well, because p is greater than 1, t sub 1 is also greater than 1. But of course, we just said that 1 is equal to t0. So this means that t sub 1 is greater than or equal to t sub 0. Right, so this gives us the base case. All right, so again, the way that we just did this was we just kind of explicitly worked out what t sub 1 was, and then just checked things, and things do work out. So we do have our base case here. All right, so questions so far? Okay. So again, proposition Pn is true when n is equal to 0. So now let's just go on. Let's just write our boilerplate. So let's assume our inductive hypothesis. So let's say that P sub n is true for some n equals m. And let's try to run through the inductive step. So let's write n as m plus 1. Okay, so the proof by induction is going to be a little bit weird here, so I'll try my best to walk you through it. Now, if we go back to the inductive hypothesis, then we see that T sub m is positive. Actually, it's greater than or equal to 1, but at least we know that it's positive. So that means both P times Tm plus P is positive and Tm plus P are positive. All right, so again, we know that T sub m is positive because by the inductive hypothesis, T sub m is greater than 1. So we know that both of these are positive. And so then this means that what we're calling T sub n, that also has to be positive. So again, T sub n, which of course is T sub m plus 1, I can write as the ratio of these two, right? The ratio of two positive numbers. So I know now that T sub n is positive. Right, so that's going to be one of the first things. So the first thing I wanted to point out is that T sub n has to be a positive number. That's before I can go any further in proving the rest of this. Okay. All right. Now next, I know by the inductive hypothesis that T sub m squared is less than P. Right, that was part of the inductive hypothesis. T sub m squared is less than P. So now let's take a look at the next term in the sequence, T sub m plus 1 squared. So here's the formula that you'd have to work out. You just simply prove that P minus Tn squared, right? Remember, I'm going to substitute in the expression from before. That looks like the following product of three things. So this is just some algebra. Use the fact that Tn, you can write this as like this P, Tm plus P divided by Tm plus P. And you just prove that it's the product of these three. So the first one here, of course, is non-negative because P is greater than 1. The second one here is non-negative because of the inductive hypothesis. And the third one here is non-negative because, well, Tm is positive. So I have the product of three positive things, and that should be positive. That's the idea. So Tn squared is less than P. That's the whole point here of what we just done. Okay, so again, Tn squared here is less than P. So now we've just proven two things. So first we proved in the first part here that Tn is positive. Here we proved that Tn squared is less than P. So now we can kind of do the rest of this. So finally, I see here that this difference is positive. So again, this is a formula that you have to work out. So Tn plus 1 minus Tn is the product of this thing here, which we just said is positive, and this thing here is positive because Tn is positive. Right, so we just proved that this is positive and this is positive. So the difference here has to be positive. But now that difference being positive is exactly this here. So this is what it means to be an increasing sequence. Right, so again, here we have an increasing sequence. So that means that our P sub n is true for the next case. And so then here's just our boilerplate, just to put it all together. So we just conclude that because Pn implies Pn plus 1, then the statement has to be true for all non-negative integers. Okay, so any questions about this first half here? Right. Okay, well now let's just try to maybe do the second part. And for the second part, we had to say something about absolute, or should I say about how it's related to epsilon. So I just want to remind you that if we make this substitution here, then we have the following identity. So I said this on the previous slide, but I just want to remind you that this is what we have. All right, so just an identity, it's just algebra, you just kind of work it out, play around with it. Now for the second statement, I need to show something about my inequalities involving epsilon. So that's why really we're just going to work through a series of inequalities here. So first we have this identity. This is just algebra. You just kind of plug in Tn plus 1, you get this. Next, we have the following inequality. And this is because of a couple of things. Let's see. So sorry, I think this should be an n, so this is a typo. Well, we just proved that our numbers are positive. So that means then we have the following inequality. Right, so if we have something positive, then we have this inequality here. And again, I've written here m, but this should be n. So we can now say that I can replace this denominator with just the number p squared. Right, so again, that's the next part of the inequality. I can replace this denominator with the number p squared. Okay, all right, so I'll keep going here. Now, remember that we were trying to say something here about if Tn is close, then what happens in the next case? Right, so here, if Tn is relatively close to p, Tn squared is close to p, then I'm going to replace this here with the epsilon here. Right, so again, when I've written m here, it should be n. Okay, and so then finally, I just do a little bit of algebra, and I realize that if I just replace this thing here with 1 minus 1 over p, then I see that this here, of course, is just equal to this here. Right. So to kind of recap, what we've now proven is that if Tn is relatively close to epsilon, then this Tn plus 1 is actually even closer to epsilon. Right, and of course, that's exactly what we wanted to prove in the second statement, that if Tn squared minus p minus Tn squared is close to epsilon, then Tn plus 1 squared minus p is even closer to epsilon. Okay, any questions so far? Okay, I'm only gonna quickly skim over the other direction of the proof because it's not really worth it to go through, but it just says that it's gonna be very, very similar. So essentially just do it by induction. You have to take a look at the statement here that is decreasing. And so you just kind of work it all out almost exactly in the same way. All right, so again, I'm not really gonna worry about this because I'll just leave it for the lecture notes just to say that this is the whole point. All right, so to recap, this is now what we've done. And I do want to come back and talk about this more on Friday. So if you wanted to compute square roots, here's how you would do it. Here's how you do it like in a very realistic sense. So of course, we really want to talk about the square root if p is greater than 1. So this first says that I can define a sequence in this way. And this will be a monotone increasing sequence. Right, so it'll approach getting larger from below. And then these other two statements here just say that it's going to converge to the square root of p. So I haven't just written a really silly sequence. It actually is going to converge to the square root of p. On the other hand, I can define a sequence in this way here. And this will be a monotone decreasing sequence. So it starts from above and then goes down to get smaller and smaller. And in a similar way, this here will now get closer and closer to the square root of p. Right, so we've actually proven that in both cases that the limit actually is going to be the square root of p. Okay, so any questions for what we've done today? Okay, well, all the slides will be here online. So what I'll end up by saying is please remember that the next homework assignment is going to be due on Wednesday. And on Friday, I want to spend some time going over some of the previous problem sets. So some statements that we had about the lim sup, or sorry, the supremum and the infimum, and then what we know about the square roots. Right, so we'll talk about that on Friday. Okay, all right, so have a good rest of the day and see you in a couple of days then.
Professor, do you still have time for questions?
Do I have time for questions?
Yeah.
Yeah, I do.
Okay, so I only have one question for the monotone convergence theorem. So it says that if I have a monotone increasing or decreasing sequence with an upper bound or a lower bound, then it converges. Does this say that it converges to the supremum or infimum?
That's right, it does, because that's part of the proof.
Okay.
So that it will always converge to either the supremum or the infimum, depending.
All right, thank you.
Okay, you're welcome. Okay, all right, we'll see you all later then.
I have a question.
Oh, sure.
Wasn't the next homework supposed to be due on Friday, not Wednesday?
Well, homework 9, I believe it is due on Friday, and then homework 10, I don't remember the numbers right in front of me, but they're due Friday and Wednesday, respectively. So the next one's be Friday, and then the one after that's going to be due on Wednesday.
Okay, I got it. Thank you.
Okay, you're welcome.
Professor Goins, do you still have office hours?
I do. Yeah, I'm just going to log off here and then log in for office hours.
Okay, cool.
Okay, all right. See you then.